Good morning, everybody. Thank you for being here to join this presentation. I know end of July is a period for vacation for a lot of people, but we had the opportunity to have Luis now presenting today. Luis has been, he finished Texas A&M in 2015. He studied the geophysics there, and then he moved to SMU, where he works with Heather Desson, and he finished his grad school in 2018, and he's about to finish this next month his PhD as well at SMU, which is actually for which he has been awarded a fellowship from the SMU University in 2018. Luis is working in the area of Texas, mostly in the DFW area. He collaborates with the Bureau as well, being part of our BGSMU group working in the area funded by TexNet. And also he has been recently working also in some data set from Oklahoma. Today he's going to present the tracking induced seismicity in the Fort Worth Basin in the Texas and also in northern Oklahoma using local arrays and large M-style arrays. It's the work that he published for the DFW, working on the data set from 2008 to 2020, and some of his recent work also with the large M-style array that was deployed in Oklahoma a few years ago. So thank you, Luis, for being available to present. We can start the presentation now.
All right. Thanks for the introduction, Alexandros, and hello, everyone, and welcome to my presentation, where I'll be going over the work I've been doing in conjunction with TexNet and the Bureau, as well as a little bit of the work in Northern Oklahoma. So to start with, I think it'd be good to introduce myself. My name is Quinones, and I'm an earthquake seismologist from SMU in Dallas, Texas, where I've been cataloging and analyzing induced seismicity sequences, which have been occurring in the central US with a particular focus on the Fort Worth Basin earthquake sequences in North Texas, although I've also been working with the wavefields dataset in northern Oklahoma as well. Generally speaking, my work has consisted of analyzing seismic data recorded from local seismic networks, both manually and using more automated detection techniques in order to create high quality earthquake catalogs to gain some insight into the processes inducing slip on the source faults of each sequence and examine how different detection and cataloging techniques perform on different array type data sets. Now, in this presentation, I'll be going over the scope of the research I've been conducting at SMU and focusing on answering 3 key questions that are primarily focused on my work in North Texas and Oklahoma, but are also indicative of the types of questions and analysis that needs to be considered when analyzing many different types of seismic data sets. The first part of my talk will focus in on my work creating a historical catalog for the Fort Worth Basin and answering the general question about what this specific region of seismicity might be telling us about induced seismicity as a whole. Next, I'll focus in on one specific sequence from the Fort Worth Basin, the Dallas-Irving sequence, telling you about what makes it interesting when compared to the other sequences in the basin, and about the work done to answer key questions about what stress changes might have induced slip on its source fault. Lastly, my talk will shift its focus a little bit to talk about some newer earthquake detection techniques, which I've begun to utilize in both North Texas and Oklahoma, and I'll talk about their usefulness in monitoring and creating earthquake catalogs efficiently and rapidly. Now, to introduce seismicity in the first study area, the Fort Worth Basin, North Texas. Now, since 2008, seismicity has been occurring at numerous locations throughout the northeast portion of the Fort Worth Basin. And several studies of the Fort Worth Basin seismicity have examined the spatial temporal correlations between seismicity and fluid injection activities within the basin, which began with the shale gas boom in the mid-2000s. These studies concluded that injection-related increase in pore fluid pressure are the main driving stress changes inducing seismicity at sequence sites such as the Venus earthquake sequence in northeast Johnson County. However, questions remain about how far do the fluids and their associated stress changes propagate away from the injection well locations. Additionally, seismicity occurring within the Dallas-Irving sequence right here in Dallas County remains an open question due to there being no injection activities occurring at close distances to those earthquake sequences. Now I'll quickly go over a bit of the geology of the basin for context, using a cross-sectional line going for the northern part of the basin shown by the red line. Now, the Fort Worth Basin is a foreland basin formed during the Ouachita orogeny around 300 million years ago, which is bounded to the east by the Ouachita Thrust Fronts, to the north by the Munster and Red River Arches, and to the south by the Llano Uplift. Production-wise, the Barnett Shale Formation is the most important formation, as it was one of the largest unconventional natural gas plays in the United States. Now, as the Barnett Shale, which lies around 2.1 kilometers in depth, is an unconventional natural gas play, as I said, it requires hydraulic fracturing techniques to extract the natural gas, which produce large amounts of fluids that need to be reinjected. In the Fort Worth Basin, the Ellenberger Limestone Dolomite Formation, which lies around 3 to 4 kilometers in depth in this part of the basin, is the main fluid disposal unit. Now, importantly, production-wise, the basin's eastern boundary, where the Ouachita and the Ellenberger Formation meet, is also considered the edge of the Ellenberger, where the formation is no longer hydraulically connected due to a series of boundary normal faulting structures along the eastern boundary of the basin. Additionally, the Ellenberger is also hydraulically connected to the crystalline basement formation for a series of faults which cut through the various formations in the basin. Now, the monitoring and seismic history of the Fort Worth Basin since 2008 is quite complicated due to a variety of factors. And so a lot of my work has been focused on gathering the various seismic data sets that were recorded using SME stations throughout the years, which involved a mix of different station types ranging from temporary single component sensors to more permanently installed broadband stations. Now, the amount of stations that are actively monitoring the basin has changed to reflect the changes in seismicity rates throughout the basin, where during the period of peak seismicity, there was as many as 50 sensors active across the basin, but as the seismicity rates have gone down in recent years, so have the number of stations, with around 30 sensors still being in place as of today. Now, the final combined earthquake catalog that was created from SMU's data of the basin-wide seismicity was known as the North Texas Earthquake Catalog, and covers seismicity from 2008 to the present day. Although if you were trying to get the full picture of the seismicity occurring in the basin, you'd have to also look at a couple other catalogs of seismicity due to there being a period of time when SMU didn't operate any stations from about 2010 to 2014. To try and illustrate the catalog over time, I have an animation I'd like to show. Now, this animation shows the history of seismicity in active SME stations of the basin throughout time. Now, the first earthquakes to have occurred in the basin, or at least been reported in the basin, occurred at the DFW airport sites and were reported by the USGS, which prompted the first deployment of stations to monitor seismicity there by SME shortly afterward. Following another fault becoming active in the south, though we entered a time period where SMU didn't operate any stations. However, just because SMU was not operating any stations doesn't mean that there weren't any earthquakes occurring, as there were several events recorded in what is called the Froelich Earthquake Catalog, which was created using the TA array stations as they passed through the basin, and the USGS permanent stations, which recorded several events throughout the basin. However, it was only in late 2013 that SMU began to place stations to monitor the Azle sequence in the northwest, the Dallas-Irving sequence in the northeast, and then again later in 2015, the Venus sequence in the southeast, using their own smaller local monitoring stations. And since then, SMU has continued to record and catalog seismicity throughout the basin as even more faults became active. Although since 2016, seismicity rates have decreased. So again, as the animation plays, we saw that DFW airport sequence was the first to become active, and we entered this period again when SMU wasn't operating any local stations, but the USGS continued to report seismicity. This all began to change when a large amount of events, felt earthquakes began to be felt in Azle, prompting a local network to be deployed. This was followed by the Dallas-Irving sequence, following a pair of magnitude 3.5 plus events, and the Venus earthquake sequence and monitoring network, again in later 2015, following a magnitude 4 events. And since then, you can see that different other faults have also become active throughout the basin. And you can also see from this chart right here, this dashed line representing injection rates, that injection rates peaked around 2012 and have since then been slowly falling off. Although this time period right here at the end, when injection rates really fell off, is just a period of time when I don't have as much injection volume data. Now, the SMU North Texas earthquake catalog can be separated several different ways. Here, I'm showing the catalog separated out by which earthquakes correspond to which active fault. When examining each of the sequences temporally, we see a mixture between faults which display more swarm-like behavior, like the Venus earthquake sequence, which has shown numerous small swarms throughout its history, while the Dallas-Irving sequence seemed to display more traditional main shock, aftershock characteristics, with most of its recorded seismicity occurring after the pair of 3.5 plus events, which occurred in early January 2015. It should be noted that the temporal distribution of events in the North Texas catalog is incomplete, as the local monitoring networks around each of the named sequences were only put in place after the sequences had already began and were producing felt earthquakes. So we don't have exact estimates of when each of the sequences actually began in the specific North Texas earthquake study catalog. Now, when we examine the spatial distributions of each of the named sequences, which had local networks monitoring them, we observed that the sequences are occurring along individual faults and that the earthquakes are concentrated within the crystalline basement, which, as I discussed earlier, lies beneath the main fluid disposal formation in the basin, the Ellenberger Formation, as you can see from these three little cross-sectional views right here. Now, the main exception to this depth rule is the Azle sequence, which does have many earthquakes recorded within the Ellenberger, which have been theorized to either be from an antiphytic fault to the main Azle fault, which may have been activated due to the failing of a karst-like structure within the Ellenberger, or due to uneven loading of the formations related to injection and production activities and poroelastic stress changes. There are other named sequences like the DFW Airport and Cleburne sequences, which are shown here in these blue circles, along with a newer activated fault in near the Fort Worth area, which also show primarily basement-based earthquakes, but their depths are not as well constrained due to a lack of stations right on top of the faults. The other key factor is that the sequences occurring along the eastern margin of the basin are occurring beneath the Ouachita thrust front feature, and so have a different overburden pressure profile when compared to the western activated faults. Now, I created a catalog of focal mechanisms for the Fort Worth Basin earthquakes using data collected from three sequences which had good azimuthal coverage of the events from their local networks. Due to these being mainly very small magnitude events, I had to create the focal mechanisms from using both P-wave first motion and S to P-wave amplitude ratio data to compensate with the focal mechanisms being created using the Hardbeck and Shearer hash software. When plotting the full focal mechanism catalog using these ternary plots, we can see that each of the sequences are occurring along primarily normal faulting structures. And when plotting the strikes and dips of the faults, we can see that they're mainly northeast southwest trending normal faults. The Azle sequence is a bit of the odd man out here, however, as it had far fewer focal mechanism solutions, which are also of lower quality due to a lack of good station coverage during its period of peak seismicity. The Azle sequence is also, again, the only sequence of these three to be occurring in the more western part of the basin and not underlying the Ouachita thrust front facies. Now, I used the focal mechanism catalogs to conduct a formal stress inversion to define what the local stress field during the period of seismicity was for the western and eastern portions of the basin, and found that both parts of the basin are within a normal faulting stress regime with a maximum horizontal stress in the northeast southwest direction, which is consistent with other measurements of maximum horizontal stress, which we're calculating using borehole breakout data and other studies. The main differences across the basin are some slight differences in the orientations of the principal stresses, but using these principal stress orientations along with estimates of the overburden pressure calculated using the geology and Nafe-Drake curve approximations of density at the sites of each of the induced seismicity sequences does allow me to create a full stress tensor for each of the sequences. Now, those full stress sensors are plotted here as 3D Moore circles of effective normal and shear stresses, where I've also plotted the fault plane solutions from each of the focal mechanisms within the 3D Moore circles. And what we can see here is that most of the focal mechanism solutions represent faults that would be critically stressed within the regional stress field calculated using the focal mechanisms. And the overall magnitude of stress changes that would have been needed to induce slip on these faults is very small. And these magnitude of stress changes may have already been recorded in the area around the Venus earthquake sequence specifically, where fall-off testing found that the Ellenberger Formation had already become overpressured during the period of seismic activity of that fault. Now, to wrap back around to that first question, what can the earthquake sequences in the Fort Worth Basin tell us about induced seismicity in general? Well, we can see that most seismicity in the Fort Worth Basin is concentrated in areas near the injection wells and occurs within the crystalline basements characteristic of fluid injection induced seismicity. We can also see that the proximity between the wells and seismicity suggests that direct pore fluid pressure diffusion is the main driving force of induced seismicity at a lot of the earthquake sequences, and that the focal mechanism solutions and stress inversion results suggest that the active faults in the basin were critically stressed and thus were primed to slip. Now, for the next part of the presentation, I want to focus more on the Dallas-Irving sequence in particular, as it is true that while most of the sequences in the basin have that smoking gun nearby injection well, which can be pointed to as the source of the stress change needed to have induced slip, this isn't true for the Dallas-Irving sequence. Now, in some regards, the Dallas-Irving sequence is the most important sequence to be occurring in the Fort Worth Basin because it's the earthquake sequence occurring right in the middle of a major metropolitan area, in a city which absolutely has not been built to withstand any degree of ground shaking. And the Dallas-Irving sequence is also one of the most interesting sequences in the basin because unlike so many of the other sequences, it lacks that nearby injection well to provide direct pore fluid pressure changes. So the question becomes, where did the stress changes needed to have induced slip on this fault come from? One possible answer is, of course, more far field stress changes are the cause, such as proelastic or basin-wide pore fluid pressure changes due to the mass injection of fluids into the Ellenberger Formation induced slip on this fault. And so to try and estimate what these basin-wide injection-related stress changes were, I and many others sought to create geomechanical models to examine this specific effect. Now, prior geomechanical and hydrogeological models have been created to examine injection-related stress changes within the Fort Worth Basin. The model created by Zhai and Shirzai, shown here, was a coupled pore fluid pressure model and Proelastic geomechanical model, which found injection-related stress changes to be clustered at sites of high volume injection activity and found little to no stress increases in the Dallas-Irving site. But this model was created prior to the creation of new geologic geometry and fault maps for the Fort Worth Basin, and so does not take into account aspects of the basin such as the dipping geologic formations or there being a dense basement-rooted fault network being present throughout the entire basin. Now, the second model shown here is a hydrogeological model created at the BEG, which was examining pore fluid pressure increases throughout the basin and does incorporate the updated geologic formation and fault network maps for the basin. However, the model is not coupled to solve for any proelastic stress changes. What I'm going to show you here is our COMSOL constructed model, which is coupled to solve for both pore fluid pressure and proelastic stress changes, and utilizes many of the same data sets as those used in the construction of the Gao and Nicole model. Now, the model space being created here is a 100 square kilometer block representing the northeast portion of the Fort Worth Basin, where most seismicity and injection activities are actually taking place. The model geometries of each of the major formations are based off formation top data constructed using the available well log data, with the most important units under consideration in this model being the Ellenberger limestone formation, which again is the main fluid disposal formation of the basin, and the crystalline basement formation where the majority of seismicity is actually taking place. The key feature of using the updated formation geometries is to consider the northeast dips of each of the major formations within the basin, which are converted into 3D model geometries within the COMSOL software, shown here with a very large amount of vertical exaggeration to actually be able to see the dip over the large spatial area. Now, the second major geometric feature of the model is the newly created fault map for the Fort Worth Basin, which was created using a mixture of well log, 3D seismic reflection, and earthquake location information were available across the entirety of the Fort Worth Basin. This new fault map consists of 111 basement-seated faults, which extend into the Ellenberg Formation and which are treated as having uniformly set high permeability damage zones on the order of about 1,000 millidarcy and damage zone widths of about 100 meters. I chose a uniform set of damage zone widths due to there being a lack of data, specific data about the width of each of the damage zones for each individual fault. Now, the 3D geometries of each of these faults were constructed within the COMSOL modeling software using the same fault data described within the Hennings 2019 publication. And lastly, I integrated the injection volume data compiled by the Texas Railroad Commission. This fluid injection volumes are annually reported as monthly injection volumes for each well in the basin. In total, around 1.7 billion barrels of fluids have been injected into the Ellenberg Formation, with peak injection activity occurring around the 2011 to 2012 time period. Although as shown here, most seismic sequences in the basin only became active after this period of peak injection activity. Lastly, the gray portion of the plot here represents the period of time for which a large portion of the wells have not reported their injection volumes yet. Ultimately, in the current version of the model, I discretized the model space into 1 square kilometer cells for the purpose of constructing the injection wells and used monthly injection rates within the actual model to calculate the injection associated stress changes. Now, the full constructed 3D model is shown here with the different layers of the model representing the different major geologic units within the basin. The outer edge of the model space shown here represents a series of open flow boundary conditions where the outer limits of the model space are treated as being infinitely long, allowing for the long distance dissipation of injection-induced stress changes as they propagate to extreme distances, and so they can go back to being zero at those extreme distances away from the wells. The model view on the right shows the view from the top of the Ellenberg Formation, where the lines represent the faults and the open circles represent the injection wells. Now you can see that there are areas within the model where there are no map faults at all. In a majority of these areas, this isn't because we know for a fact that there are no faults there, but rather that there was just no data available in these areas to actually interpret any fault geometries from. Therefore, the fault maps used within the model represent the highest quality fault interpretations currently available, but there are regions of the basin where there may or may not be faults that could be incorporated into future versions of these geomechanical models. Now, again, our focus is on understanding how injection-induced stress changes propagate away from the wells and how they might affect the seismically active faults of the basin, namely the Venus and Dallas-Irving earthquake sequences shown here, which occur mainly again on that eastern boundary of the basin. Now, the pore fluid pressure results from the top of the Ellenberger are shown here with the animations on the left showing the monthly model results from the start of 2005 to the start of 2019, for which I had a good amount of injection volume information to model with. And what we can see here in the end model result on the right is that the high volume injection activities and associated increases in pore fluid pressure are concentrated in the southeastern and western portions of the basin. And the stress changes are concentrated in those areas of high volume injection activities. The stars shown here on each of the model views represent the Azle-Reno earthquake sequence in the northwest, the Dallas-Irving sequence in the northeast, and the Venus earthquake sequence in the southeast. And what we can see again is that the pore fluid pressure increases related to the injection activities are more highly concentrated in those areas of high volume injection activities, like near the Venus earthquake sequence. And the Dallas-Irving earthquake sequence does not see as large stress changes around the area of its source fault. Now here, I'm now showing both the pore fluid pressure and proelastic stress changes associated with the basin-wide injection activities across a cross-sectional line from at a depth of approximately the Ellenberger basement contact point in this portion of the basin, from the Venus earthquake sequence to the Dallas-Irving earthquake sequence. And what we can see when we plot the modeling results across time is that the pore fluid pressure increases are of a larger magnitude than the proelastic stress changes, and that even though the injection rates in the basin are much lower than they were in the past, that the injection-related stress changes are still increasing over time. Now, I want to zoom in onto the Dallas-Irving sequence site, where even though the stress changes are going to be very small, I still want to examine the relationship between the onset of seismicity at the Dallas-Irving sequence site and when exactly the stress changes began to reach the Dallas-Irving fault. Now, the model results at the Dallas-Irving sequence site are shown here on the right, which you can see that the injection-related stress changes are very small in my modeling results. However, when we plot the recorded seismicity from the Dallas-Irving sequence on top of the time series, we can see that the earthquakes only began after the stress changes would have reached the fault based on the modeling. Now, the actual magnitudes of the stress changes observed across the basin in the COMSOL model are mainly controlled by the bulk permeability value used for the Ellenberger formation, as that, along with the faults, is what the fluids use to diffuse across the basin. And what I mean by that more specifically is that when I change the bulk permeability of specifically the Ellenberger formation, that has the largest and most significant effects on both the spatial distribution of the pore fluid pressure and proelastic stress changes, and also has the largest effect on the overall magnitudes of those injection-related stress changes, where when the Ellenberger is treated to have a bulk permeability value of 1 millidarcy, the pore fluid pressure changes at the specific injection well sites reach extremely high values of over 8 megapascals, while in the 10 millidarcy case, most of the wells peak out at a little over 1.3 megapascals in pore fluid pressure changes. And in the 100 millidarcy case, none of the wells even reach 1 megapascal. Now, the reason I had to test out different bulk permeability values for the Ellenberger formation is that within COMSOL, in order to define different regions of a specific formation having different permeability values, that would be more realistic for the Ellenberger formation, as the different smaller sections of the Ellenberger would have different permeability values, and the overall spatial distribution of those permeability values would be far more heterogeneous to be more realistic. That would require the definition of thousands to hundreds of thousands of manually defined geometric objects within my model, which just wasn't feasible within the time constraints of my research to try and implement within the COMSOL modeling software. So instead, I had to rely on estimates of what I believe to be the bulk permeability of the Ellenberger formation to actually be. And going off of the seismic data and also the fall-off testing data that I had available to me from the Venus earthquake sequence sites, the bulk permeability value which best matched those data sets to help match my modeling results to observed results of those two data sets in the basin was the 10 millidarcy case. Now, when I compare our modeling results with those of the pore fluid pressure changes model made by Gao and Co., we can see that the spatial distribution in our modeling results is very consistent, but that their model results show higher magnitudes of stress changes. Now, again, this might be due to two key different factors in how our models were created. One, that our model does account for proelastic stress changes. And again, two, that their model using the Petrel software system does allow for a heterogeneous creation of permeability values for the Ellenberger formation. However, again, in both models, we do see that there is some degree of basin-wide injection-related stress changes, including at the site of the Dallas-Irving sequence, and that seismicity only began after the stress changes reached the source fault, or so we might believe based off of the North Texas Earthquake Study catalog. Now, we can recall that there is missing information on when exactly the Dallas-Irving sequence actually began, since the network of stations meant for the purpose of monitoring the sequence was only installed after felt earthquakes began to be reported in the area. In fact, if we look at the USGS earthquake catalog, we can see that there were many events being reported around the time period before the local Dallas network was installed, with many of those events having locations close to where we would later define the Dallas-Irving fault to be. Additionally, first ran template matching approaches on some of the regional USGS stations revealed that there may have been earthquakes occurring at the Dallas-Irving sequence site as early as November of 2013. Now, these prior template matching results were based off USGS station data and lacked a lot of the data that has been collected since then about the Dallas-Irving sequence. So here, in order to try and determine more information about when exactly the Dallas-Irving sequence began, and to help the overall completeness of the catalog, I'll be using the earthquake correlation scan template matching codes to perform template matching using the SMU networks in our catalog of events. So I've previously talked about the overall complexity of the monitoring efforts in the Fort Worth Basin due to an ever-changing amount of active stations and monitoring networks. What this means is that the implementation of the earthquake correlation scan template matching is not going to be simple and will require collecting a set of templates that can account for the various time periods of monitoring activity for the Dallas-Irving sequence. In plain terms, this means having a set of templates that corresponds to the pre-2015 local network deployment, which will utilize regional station event template match-based approaches. Now that was a lot, so let's get back to the original question and see what we've read, or see what we've gathered about these different studies relating to the Dallas-Irving earthquake sequence. So what makes the Dallas-Irving sequence unique when discussing induced seismicity, and what were the main contributing stress changes that induced slip on its causative fault? Well, the Dallas-Irving earthquake sequence is the only named earthquake sequence within the Fort Worth Basin to not have a nearby injection well, which could be directly associated with the induced seismicity. However, modeling results agree that although the basin-wide injection-related stress changes are small in magnitude at the Dallas-Irving sequence site, that these basin-wide stress changes have affected the source fault of the Dallas-Irving sequence. And the Dallas-Irving sequence may be an example of potential seismic hazards associated with far-field injection-related stress changes, which need to be considered when performing fluid injection activities. And lastly, while the exact start date of the Dallas-Irving sequence remains unknown, template matching-based techniques have allowed us to gain further insight into the pre-local monitoring network period of seismicity at the sequence site. Now, we've hit a kind of limit of what different detection and location techniques are really feasible using the North Texas data sets. We could run a machine learning approach to, again, try to fill out our catalog data sets, but another group is already in the process of doing that type of analysis. And taking a step back, while the North Texas data set has its strength, is in its longer timescale of seismic monitoring when compared to many other data sets of induced seismicity. At the same time, it's not wholly representative of what all modern network deployments are designed like nowadays, and for which a number of newer detection techniques are designed to be used with. Therefore, to help us answer our final question that I introduced at the beginning of the talk, we have to say goodbye to Texas for a little bit and look a little north towards Oklahoma. Specifically, I'm going to be talking about the Community Wavefields Demonstration Experiment Array dataset, which was installed back in 2016, which was comprised of a mixture of over 360 free component nodal stations and 18 broadband sensors in an area experiencing induced seismicity, and which was created for the purposes of examining the full wave field in a set of separate studies. Here, my interest lies in the fact that the array reflects a more modern defined array dataset, which contains a densely spaced network of stations that, while the nodal stations were only in place for a short period of time, a little under a month, still reflects a dense network dataset that is necessary for a lot more modern detection algorithms and techniques to be able to be used. Now, one issue with the wavefields dataset is that there previously had been no published catalog whatsoever created using the data catalog collected from the array yet. So I attempted to use the nodal dataset along with an automated detection technique to create this first run earthquake catalog for the Community Wavefields Demonstration Experiment, which can be seen here. And again, the earthquake catalog creating using this data set is an example of fluid injection induced seismicity, where the majority of seismicity is concentrated within the crystalline basement. However, the differences between this area, northern Oklahoma, and the Fort Worth Basin is that there are numerous different smaller fault segments that have become active in a much smaller spatial area compared to the Fort Worth Basin. And the stress regime in this area, in this location, is a strike slip stress regime with a maximum horizontal stress orientation in a more east-west orientation. Simply put, we are dealing with earthquakes occurring on several different faults during this narrow time period, which are occurring within the crystalline basement and which exhibit behavior consistent with fluid injection associated induced seismicity in this part of Oklahoma. Additionally, we're dealing with typically very small earthquakes during this time period, and we're going to be focusing in on our efforts on the local earthquakes around the array. Now, there are numerous different methods that attempt to take advantage of having a densely spaced network of hundreds of sensors in what are considered large N-style arrays. Here, I'm going to be testing the feasibility and usefulness of using the local similarity technique to test the method's ability to create a rapid detection list and possible initial earthquake catalog using the nodal instruments for the purposes of using this generated earthquake catalog as a first run version that could be then be improved upon using other methodologies, but which would serve its purpose in allowing an analyst to quickly focus their searches for possible events to review within a catalog. The main idea behind this technique is to stack waveforms across the network in order to help boost the signal to noise ratio of the signals, wherein signals captured across the stations that are very close to one another will have strongly correlated signals, but their noise will be far less correlated. The methodology I'm using comes straight from the initial source publication for the method, wherein we take each individual station in the network and find a defined number of nearest neighbor stations. Here I'm defining 4 nearest neighbors, and stack their waveforms to create what's called a local coherence value. Then once that process is done for each individual station in the network for a period of time, all those individual local coherence datasets are then stacked from across the entire network to create a network local coherence signal, where again, the correlated signals from across the network should be much stronger than the random noise recorded. Lastly, we define a detection threshold value based off of the median absolute deviation value of the stacked local coherence over a defined time period and use that as our event detector. Now, what makes the local coherence technique so efficient is that it makes no assumptions about the geology or physics of the region of interest, instead only examining the process waveform data collected by an array, determining if an event was actually detected. When writing up these codes using a mixture of Python codes using OpSpy to gather and process the waveform data, and built in Python to C compilers, I was able to process the entirety of the nodal wavefields array dataset of over 360 stations in less than 48 hours, using the high performance computing hardware available to me at SMU. An example of 1 hour's worth of data from the vertical channel of the nodal stations is shown here, where you can see several different peaks in local similarity value across time, which can be used to define the event detections. At the top, the circles represent the event detections over the same hour's worth of data that were made using a standard STA LTA auto detector, and those captured by a human analyst. The figure on the right is a zoomed in version of the stacked local coherence from a different point in time that shows 3 separate event detections which occurred very close in time to one another, with the waveforms collected from across the nodal array shown here as well, where you can see them move out across the array as the signals hit stations. And you can sort and you can begin to see what the local similarity is actually representing is this coherence of the signals across the network as the phases hit and travel across the network. Now, in total, the local similarity technique was able to detect far more events when compared to the human analysts. However, many of these event detections come from outside of the local areas surrounding the array, and so were included in the original benchmark catalog that was created using more traditional techniques. In order to account for this, we ran the local similarity analysis using both the vertical and horizontal channels in order to capture both P and S wave detection times across the nodal array. Now, the local similarity technique does not calculate individual phase arrival times across each individual station, and instead just outputs a single event detection time for the entire array, which could be associated with either a P or S wave arrival, as even when using the vertical channel only, you may be gathering an S wave detection or vice versa on the horizontals, and just not realize it unless you have the data from both channels. Therefore, I ran a local similarity on all 3 components and made the assumption that the vertical channel would gather more P wave detections and the 2 horizontals would gather more S wave detections. And then just ran a sort of base type of associator looking at the detection times from the verticals and horizontals to try to get a list of event detections that would have both an assumed P and S wave arrival using the 3 components of the stations. And by having the both P and S wave arrivals associated with the same detection, I could then have an S minus P time estimate, which can give me insight into whether I thought an event detection was made from a local earthquake or for much farther distance regional events. To go back to that initial question about the cell techniques, how can template matching or large N array based earthquake detection techniques help us focus our monitoring efforts? They can help us by allowing for the rapid analysis of these large data sets, which just aren't feasible for a human to complete in a decent amount of time, by first allowing us to quickly focus on key portions of the data set, and when used in combination with other automated techniques, become able to generate an initial earthquake catalog far quicker than when using more traditional techniques, which can then be iterated upon and improved using other catalog analysis techniques such as double difference relocation or incorporating more machine-based learning approaches using the initial catalog. And that brings me through to the end of my presentation and the work that I've been completing in the Fort Worth Basin and northern Texas, where we saw that the Fort Worth Basin is a prime example of fluid injection associated induced seismicity, which contains examples of both near and far field pore fluid pressure and proelastic stress diffusion, which may have been inducing seismicity on faults all throughout the basin. We saw the Dallas-Irving sequence, which carries the highest seismic risk of all the sequences within the basin, is an example of an active fault, which displays all the behavior of an injection-induced seismic sequence, but lacks a direct nearby injection wall, meaning that basin-wide stress changes are the most likely source of the stress changes that induce slip on that fault. And when dealing with more modern array types with far higher numbers of stations, it is necessary to use modern detection techniques to focus analysis of the seismic data sets. And the local similarity technique, when combined with possible separate association and location techniques, does provide the ability to rapidly generate earthquake catalogs, which can then be further analyzed using manual or other advanced techniques. Thank you. And if, I guess now is the time, if you have any questions, feel free to ask.
Thank you, Luis. That was really a great presentation. Dino has a question. Dino, go on.
Yes, great talk. I have a question. Can you go back several slides by comparison between the human analysis and the STA, LTA determination? Yep. Yes, exactly. So it looks to me like the difference between the STA over LTA and the local similarity analysis is that the number of events it can be detected. So my question comes to this is, the difference between number can be detected will impact your future interpretation, or it doesn't make any difference?
So the number of events detected increasing using local similarity versus STA LTA can and cannot have an effect. So the assumption would be that the STA LTA is detecting fewer events, but the events detecting are larger magnitude events or more easily detected events when compared to local similarity. So it can affect the analysis when looking at catalog completeness of the array. So when trying to do some catalog statistics such as B-value approximation, and also just looking at the entire history of seismicity, it could mean that some potential earlier events could be missed due to the fact that we didn't see the initial beginning of events occurring on a fault segment using LCLTA. But if it comes to more looking at seismic hazard and risk and looking where you really care more about the larger magnitude events, the increase in number of events from local similarity probably will not have as large an effect.
Okay, thank you.
Yeah.
Okay, Yang Kang, you raised your hand first, and then Peter Ehebul.
Hi, Luis. Very nice presentation. I appreciate it. I have a question about the EQ coscan, the technique used to detect many small hidden earthquakes. So as we know, using EQ coscan or some other more advanced deep learning-based methods will inevitably detect many more small earthquakes, but will inevitably cause more false positives. So my question is, how do you QC the results to ensure that the smallest false positives are detected?
So right now, the main quality control technique that I've used in order to make sure that these template matched detections are actual earthquakes instead of false detections is looking at, first of all, the number of phase picks that were able to be calculated using EQ core scan. Now, those phase picks from those template match approaches are calculated using the cross correlation values from the phase picks of real events that were used as templates. And it gives me a cross correlation value for every single one. And I set a threshold value of 0.6 at least in order for a phase pick to be determined to be a true phase arrival for a detected template matched event. And right now, what I do for quality control is I say that there must be at least 8 phase picks associated with a detection in order for me to consider that event to be real.
Got it. Thank you.
Yeah.
Okay, Peter.
Yeah, Louis, this is an amazing amount of work that you've done. I wonder how many PhDs you're getting for this. But you covered a lot of ground in your talk, going from the earthquakes to the basin scale, flow, and geomechanics. Very impressive. I'm trying to understand the implications of your geomechanics modeling and flow pressure diffusion modeling, and especially the difference between your results and what the Garo Nicole. So what is the effect of the proelasticity at that scale? So the work that we have done is, well, actually, Madi has also covered a large part of the basin, but overall it was more focused, right? What is the effect of the proelasticity on that earthquake sequence when it comes to this basin scale, considering that you have a comparably thin veneer of the reservoir that's undergoing the pore pressure changes, and then you have a massive basement underneath, mechanically speaking, massive, that is not undergoing that same proelastic stressing. So I'm trying to understand what the consequence of that is and how this influences the mechanics of that earthquake sequence. Since you have done the full, I don't know if it's fully coupled or not, but you have proelasticity in it. So I'm wondering how to interpret this data. I wonder if you can shed some light on that. What are your thoughts on this?
Yeah. So the model is fully coupled in this version of the model. So it is simultaneously solving for both pore fluid pressure and proelastic stress changes. Now, one of the major missing factors in this coupled geomechanical model with relating specifically to the proelastic stress changes is that production activities in the Barnett Shale are not currently incorporated into the model. And what I saw based on the controlling factors of the pore fluid pressure changes, where that was my main constraining data sets for creating the model and defining the parameters, is that the proelastic stress changes were largely controlled by the magnitude of the pore fluid pressure changes in the model, where they were strongly coupled, they were strongly correlated with one another, where specifically, again, with this parameter testing of the bulk permeability, when I decreased the bulk permeability, my pore fluid pressure results shot up. So did my proelastic stress change effects in turn. And while, again, they did limit the spatial distribution, the distance that the proelastic stress changes could propagate away from the wells, it was still much farther distance than the injection wells. So I would say that in this model, the proelastic stress changes are more a consequence of the pore fluid pressure results. They're more just directly correlated with one another, but they are smaller in magnitude across all modeling results when compared to the pore fluid pressure.
Right. So that's what I would expect overall, obviously, from the physics of how we define the proelastic stress change. The thing is, so you are modeling, so you're injecting the Ellenberger, right? But the earthquakes are primarily in the basement. Mm-hmm. So correct me if I'm correct on this, but in the Ellenberger, the proelastic stress change would actually make the faults less likely to slip in the Ellenberger. Is that correct?
Yes.
But probably more likely to slip in the basement, no? Because it's bonded, right? So the Ellenberger is bonded to the basement, but the pore pressure does not necessarily diffuse easily into the basement, or at least not very deeply. So then if you have a proelastic stress in the Ellenberger, that would actually make the basement more tensile, wouldn't it?
Yes, I do see what we would call negative proelastic stress changes in the Ellenberger, but positive stress change in the crystalline basements.
So that would be perhaps important to quantify, right? To plot, if you, I don't know, I guess the basement is included in your model, right?
Yes. Yes.
You could plot that, right? There's like a depth profile, for instance, at the where the earthquake sequence is over time, perhaps, right?
Yes.
That's something I would suggest if you haven't done it yet, or I mean, that's work that's still in preparation, right? Yes.
Yes, and that's a very good note. I need to plot that out.
Because otherwise, I think it's very hard for even for me seeing those results now is to really understand the significance of this work relative to prior work that did not include the proelasticity, right? What does it actually imply specifically? If it may be a minor effect actually, but not so sure about this actually, right? Because even if it's a magnitude less than the pore pressure, both combined, it's still part of the equation, right? So it may not be something that's just a secondary effect. It could still be important, right?
Yes. Thank you.
Okay.
Maybe,
yeah.
I don't know if Mari is still here. Yeah, but maybe he has some further comments on that.
Okay, Luis, we are at 10 o'clock, so I have a short question. I have a lot of questions actually, but let's discuss this later this week. We have the seismology group coordination meeting. So I have one question that is related to Oklahoma, to the nodes and the broadbands. You have a plot where you show the comparison between the broadbands and the yes, this one. So the results here, the detection you show here with the nodes are after stacking them, correct?
Or after what?
The results here that you show out of the nodes detections are after stacking the nodes. You stack the data, the waveform data.
Yes.
For the broadbands, I see that you have deployed, they are deployed on in triangular arrays. These detections are using triangular arrays, using all the broadbands together, or individual broadband stations?
All of the broadbands together. So when I define a broadband-based detection, that means a human analyst, myself, went through the broadband data and picked that event.
Okay, so this is our manual detections then. It's not like stacking the broadband data.
Yes, this is not a stacking of the broadband data. This is a comparison of manual, more traditional based.
But the nodes are stacking and they are automatic detections.
Yes.
Okay, I think maybe it's good to stack the broadbands and to see what is the different stuff and do the automatic again to see what's the difference. Because of course there is an effect of the number of nodes that you use, because you certainly get better data stacking hundreds of nodes than stacking tens of broadbands. But it will be nice to see the difference when you do it both with after stacking and do it automatically. I think that's something that we would like to see in the future. Maybe we can discuss offline. Okay, I have to thank Luis for this excellent presentation. As Peter said, that's not one PhD, that's a lot of PhDs, and congratulations also to the group, to Heather, that was that's coordinating this effort, and all the group at SMU. Madi, you have a question?
Yes, I have a quick question just about this CWDE catalog. So, Luis, first of all, great work. I was wondering what was the logic behind changing the SH max azimuth for around 10 or 20 degrees. I think you showed that in the previous slide. Can you explain it again? So it's very relevant to one of the test cases that we simulated for this area.
Oh, yes.
Right, and this is, yeah.
The SH max is different in northern Oklahoma to the Fort Worth Basin. It's just that the regional stress field in northern Oklahoma has rotated already So as you move north throughout the Fort Worth Basin, you begin to see this rotation from north-northeast, south-southwest SH max to a more east-west SH max, which has been compiled from borehole breakout data, focal mechanism analysis, etc. So this is just a regional SH max taken from prior literature. And these dashed lines right here represent, given that this is a strike slip stress regime, that these are the optimal fault orientations in the stress regime for failure.
So what did you do that this analysis for the area closer to Dallas Fort Worth area, or it's just for only Oklahoma, north of Oklahoma?
So I did the focal mechanism stress inversions to calculate stress field in Fort Worth Basin. I did not do that in northern Oklahoma. The northern Oklahoma SH max again is from prior other papers. Studies of northern Oklahoma and southern Kansas that already did that type of analysis, and that's the value I'm using.
Okay, thank you.
Okay, thank you guys. Have a nice rest of your day. Thank you very much. Thanks, Luis, again.
Thank you.
Bye-bye.